I have a lot of kids who tell me they love physics, but how many of them have a book at home about Einstein? If you don't have a book at home about Einstein, come on, you can't be serious that you really like physics. This one is by Walter Isaacson, and he wrote a bunch of other famous biographies, including the one on Steve Jobs. So, what do I do with my book about Einstein? I try to predict how much force it would take to lift one end. So what are you going to need to do this at home? You're going to need a decent sized book that's kind of heavy. I have here a paper clip holding the string that I've run through the middle so I can pull on it with a spring scale. I have a rubber band here holding the book together. But we're also going to need to know the mass of the book. We have 1,097 grams. Why the meter stick? It's clamped at this end. It's actually clamped over here too, so that I can make sure it doesn't go anywhere. And the reason why that's here is because if I just pull, there's nothing to stop the book from coming towards me. I need to have a pivot here, physically holding the book back while I pull this way, and then it can rotate. We have about 17 centimeters for the width of the book, and about 24 centimeters for the height. The thickness of the book really doesn't matter, except to say that it's wide enough to be stable so it doesn't tip over. Well, before I tell you how hard I have to pull, you should be able to stop the video and go do the math and figure it out. Next, you can try to figure out how hard I would have to pull if I was pulling at a 30-degree angle. That's about where I am now. And what's going to happen if I just pulled straight up? Hey, wait a minute now. Doesn't want to rotate at all. Yeah, that's because this force isn't going to produce any torque through this pivot, if that's what I want to call the pivot. But if I pull hard enough, it starts to pivot on the other side. Oh, that makes sense. So how hard would I have to pull to start it lifting like this? Well, you've got plenty of problems to work on. Now, before I go and do all this, please pause the video, try it out for yourself first. So the question is, we have to find F that's needed to tip the book. Does it make sense that the pivot is here? You can always try it and see. Yeah, that's where the pivot is. And where does the weight go? Usually right down the middle. And we'll round off the grams to 11 newtons. Well, just before this end starts to lift up, we're going to say the torque counterclockwise will be equal to the torque clockwise. The clockwise torque is going to be this weight times this distance from the pivot, which is 8.5 centimeters. The torque counterclockwise is going to be given by this force times a distance from the pivot that's perpendicular to this force. Now, where would that distance be? We're used to seeing distances being measured horizontally, but this distance turns out to be vertical. That's the 24 centimeters. Now, how do we know it's vertical? Well, the rule is that the force and the distance must be perpendicular to each other. And if I'm pulling horizontally, then this vertical distance must be perpendicular. You can also think of it as this force is missing the pivot by that distance. Well, we can fill in all the data, and we get 3.9 newtons. That is a theoretical value. Unfortunately, the spring scale read 2.8 newtons. Now, how could that possibly be? Well, there's a couple of reasons. One, the center of mass really isn't in the middle in a hardbound book for sure. The binding weighs more than this side. There's nothing here. So the center of mass is actually a little closer. That would reduce this distance, making it easier to tip over this way. Another thing is that the pivot really isn't on the very corner. It's not like we've got a hard block of wood. This fabric is a little soft back here, so it actually starts to rotate and roll a little bit. The pivot is actually all the way up here. So if you reduce this distance by making the pivot closer to here, and you knock off about 2 centimeters, which is what about I can estimate from the curvature of the book, we end up with a much closer value for the theoretical. Now, what do you think that pivot has got to do to the block to keep it from going anywhere? Again, you better pause the video first and try the problem. So if I say that this force is theoretically 3.9 newtons, that'll drag the book this way unless that pivot pushes back. And it'll have to push back with 3.9 newtons to cancel that 3.9. Now what about in the y direction? We have 11 newtons going down. There's nothing else holding it up except that corner. So what would the y component of this pivot have to be? 11 newtons. Now if you wanted to, you could go figure out the overall force and do the Pythagorean theorem and inverse tangent to get the angle. Now you've got a hard job ahead of you. Why don't you find what F is in order to start tipping this block at 30 degrees? Start by asking yourself, which of these two components produces torque about that pivot? That y component passes right through the pivot, won't produce any torque. It's all the x component. Well, we know it's 3.9 newtons theoretically from the last problem. So all you need is a little trigonometry, and you can find that the force is 4.5 newtons. And yeah, when I pulled it with the spring scale, it went way up. And does this affect the force of the pivot now? Well, not in the x direction, because that number hasn't changed. But what about in the y direction? We have 2.25 pulling up, 11 going down. The pivot has to hold up the difference. That's 8.75 newtons. And the x is still 3.9 to the right. All right, and I'll let you figure out what happens if I pull straight up. Good luck, everybody.